All right, so a nice summary of alpha, beta, and gamma. We've got the relative charge, relative mass, typical penetration, nature, typical speed, ionizing effect, and what it's absorbed by. Yes, you need to know approximately how much is absorbed. At least know that alpha are really massive, and that's absorbed by a small item like a piece of paper or some skin. And gamma can get through a lot of stuff. 2 centimeters of lead is halving the intensity. So, notation for alpha. We're going to use the alpha particle notation, which is 4,2 for a helium nucleus. Right? Or it could just be 4,2 alpha particle, because the alpha particle is just the helium nucleus. Beta decay is either going to be -1 as an electron, or it could be 0, -1 as beta. If it's beta positive, that's going to be 0, +1 electron, the positron. Gamma, we're going to just use gamma symbol, the Greek letter for gamma, lowercase gamma, or 0 mass notation, like that. Remember, math is always going to add up. Just look at your arrow here as an equal sign to see what's happening. 90 plus 2 equals 92. 91 minus 1 equals 90. 11 plus 1 is 12. 90 plus 0 is 90. Remembering alpha and beta. Plotting our neutron number versus proton number. We get that line of stability. So as you increase your neutron number, you're going to become more and more unstable. Remember that alpha decay has a mass number of 4. So that means we are losing 4 atomic mass units. So if we start out with 238, we are losing 4 because of the helium or alpha particle being emitted out. Then we have 2 protons also leaving. So you start off with 238 and 92 and send off 4,2 helium. For beta minus decay, our mass number is going to still be the same. So our mass number doesn't change because an electron, we're not accounting for the mass. Also no mass for the anti-electron neutrino. Let's go ahead and try this one. This is going to represent alpha decay of radium-226. So what's it going to turn into? We already know this bottom number is going to be 86, and this top number is going to be 222. So 86 brings us to radon. There's our radon gas. Plus, it's an alpha particle, so we have 4, oops, please don't put in that that fractional thing, helium. Sorry, chemistry teachers. So we have 222, 86, 4,2 helium. Is that it? Do we have to add in anything extra? No, we don't. This is alpha decay, so that's our complete reaction here. So 226 on the left, 222 plus 4 gives us 226 on the right, 88 on the left, 86 plus 2 on the right. All right, here's a beta decay. Try it out. Protactinium, 234. Oh, polonium is 84. Okay. Beta decay. Let's do it. Beta means we have a 0, -1. So that means this has got to be 92. This will be 234. Mass stays the same. And then we can look here, 92 is going to be uranium-234 plus our electron, It's an electron emission, so that means we have to emit an anti-electron neutrino. All right, so this tree here, this radiation tree, uranium-238 is going to become thallium, which is going to be protactinium, and then back to uranium, and then to thallium. And it's just going to keep on going as you get further and further down the tree. This happens regularly. It's what we use to be able to predict nuclear reactions, and as we'll see as we get into nuclear power plants, how this plays into it. Valley of stability, we've got our stable nuclides right near this curve of stability, which goes above the 1-to-1 ratio line here. The valley of stability in between there, we have our beta plus emitters slightly below, and then our beta minus emitters are going to be slightly above. You don't specifically have to remember that. Just remember that if n equals z, so if your mass number equals your atomic number, then you're going to be closer to a beta plus emitter. Meanwhile, if your number of neutrons is a lot greater than the number of protons, then you're probably going to be beta minus emitter. Sample question. Try it out. This is an IB question. Three particles emitted in the decay of nucleus 4520 calcium into SC, whatever that is, right? Because you don't need to know. So what we'll do is we're going to write out this reaction. 45, 20, calcium, 45, 21. All right, so we've increased our proton number, which means we need to add a beta minus particle, which is, there's our electron, so there's our beta minus particle right here. And we're also going to have to deal with the neutrino. Is it anti-electron neutrino, or is it just a regular old neutrino? Negative, negative, anti is the opposite, so it's anti-electron neutrino. Okay? So we've got beta minus, good, and the anti-electron neutrino. That one includes gamma. Alpha, gamma, anti-electron neutrino. No, alpha and neutrinos don't go together. Alpha and neutrinos don't go together. So the only one is going to be this. But that means we are emitting two types of radiation. So we have beta minus radiation, and we have the gamma radiation. So yes, you can have a reaction, and then some light is going to be given off. Whether it's visible or not is something completely different, but just know that you can have a reaction that will include beta and gamma at the same time. Could be alpha and gamma, though highly unlikely.